Quantum mechanics, the Heisenberg uncertainty principle. The pieces were now in place for a way to rationalize all these seemingly contradictory wave and particle behaviors of light and matter. But first, another weird observation. A driving force behind physics has been the criticality of making accurate measurements of physical phenomena and making predictions based on these measurements. This still holds for quantum mechanics, but with a twist. There are times when the more accurate a measurement you make of one quantity, the less accurate a measurement you can make of a complementary quantity. This is expressed in the uncertainty principle of Werner Heisenberg. Two quantities that cannot both be measured precisely at the same time are momentum and position. The more accurately that momentum can be observed, the less sure you are of where the particle is. And vice versa. The more precisely one knows where a particle is, the less one knows about its momentum. This imprecision or uncertainty is represented by delta p sub x for the momentum in the x direction and delta x for the position in the x direction. Here's the equation. Delta p sub x times delta x is always greater than or equal to h, Planck's constant. Planck's constant sets the limit for how accurate the measurements of momentum and position can be at the same time. This equation works at any scale, even that of our day-to-day lives, where we measure, for example, the positions of cars and their momenta. If that's the case, and it is, why do we feel we can very accurately measure everything we need to know about a car's size and its momentum? So why is it that if the Heisenberg uncertainty principle works in the everyday world, that we can still measure, say, the momentum and position of a car accurately? Well, the answer is because h is very small. Remember, h is 6.63 times 10 to the negative 34 joule seconds. So let's say we measure a car's position with a precision of 10 to the minus 6 meters. Well, then let's go off and calculate its momentum and find out what precision we're going to get. Well, if we use Heisenberg's uncertainty principle, delta p sub x, delta x is greater than h, and rearrange it just to find delta p sub x, we get delta p sub x is greater than or equal to h over delta x. And substituting for Planck's constant and our 10 to the minus 6 meters for the precision of our position, we get that the precision in the momentum is going to be of the order of 10 to the negative 28 Newton seconds. So an incredibly tiny number, and we don't have any instruments that can measure a car's momentum that precisely. So we don't feel any restriction from the uncertainty principle in our daily lives. Heisenberg's uncertainty principle helps us explain why electrons remain in their orbits and do not spiral down to crash into the nucleus. If an electron is confined very close to a nucleus, then the delta r, the uncertainty in the orbit's radius, will be very small. The uncertainty principle then tells us that the corresponding delta p must be very large. And if there's a large uncertainty in the momentum, then it's possible to develop a large momentum. And that means that the electron will move away from the nucleus. There is another version of the uncertainty principle which relates to energy and time as shown above. The uncertainty in the energy times the uncertainty in the time is greater than or equal to Planck's constant. This version too is always true, but again, as the last one, it is only observable in the tiny world of the electron. It doesn't impact measurements in our day-to-day classical world.